Hey guys, this is the second part of this free open response. Let's look at what they're giving us and what they're asking. All right. So, in a different experiment, the decomposition of substance Y at 50 degrees Celsius was determined to have the following rate law. So the rate law is given, and as you can see, our exponent is 2. Therefore, my reaction is going to be second order. All right. So on the axis above, sketch the graph that is expected to provide a linear relationship when plotted against time. Be sure to label the y-axis. All right, so we know it's second order, but which of the integrated expression would give us a straight slope or a straight line? All right, let's go back to our acronym CLR. C is going to be the concentration. That's going to be 0 order. L is going to be the natural log, and that's going to be first order. And R is going to be the reciprocal or inverse, and that's going to be second order. So we need the inverse. All right. So if we go back to our integrated expression, we know that 1 over the concentration of Y is equal to our rate constant times time plus 1 over the concentration of Y at time 0 or the initial. All right, so don't forget, whenever it's second order, my slope is going to be positive. All right, so let's go back to the graph that we're supposed to sketch. All right, don't forget to label your y-axis your dependent variable, and that's going to be 1 over the concentration of Y. All right. So since it's second order, my slope is going to be positive. I would have to say that my slope would look like that. Alright, so part 2, what does the slope of this line represent? The slope of this line represents my K. K is my rate constant. So you would say the slope of this line represent the rate constant with respect to second order. The rate constant with respect to second order. Rate constant with respect to second order. All right. So the temperature of the reaction was increased from 50 degrees Celsius to 100 degrees Celsius. Predict the effect this would have on each of the following. So the rate of the reaction and the rate constant, how will that affect? So the rate of the reaction, it would increase. And for our rate constant, it would also increase. And it would increase exponentially. All right, so let me delete this part. So we're going to sketch the graph, and we know that if I'm sketching the graph at 100 degrees Celsius, I know that my slope is going to increase, therefore it's going to become more positive. All right, where that is at 100 degrees Celsius, make sure we label. And this was at 50 degrees Celsius. All right, so we know that it's going to increase, but what's the why? Why will it increase? So let's go back to when we talked about the ideal gas law and the kinetic molecular theory. And we know that the kinetic energy is directly proportional to my temperature. All right, where K is going to be my Boltzmann constant. Not sure if I spelled that right, but that's the Boltzmann constant. And T is going to be temperature. All right, it's meaning that if my kinetic energy, if I increase in temperature, my kinetic energy is also increasing. All right, so what else is kinetic energy? We know that kinetic energy is also the average velocity of molecules. The root mean squared. All right, the line stands for average. So we know that kinetic energy is the average velocity of molecules. Therefore, if I increase the temperature, I increase the velocity of molecules, which also means I'm increasing the frequency that they're going to be hitting one another. All right, so we know that the concentration is going to affect my rate. If I increase concentration, I increase the rate. And also that temperature is also going to affect my rate constant. All right, so if we were to plot my rate constant over temperature, you will see that the rate is depending on temperature, and it will change exponentially. It will increase exponentially. All right. So how were scientists or chemists, how were they able to figure out and gather this data? Well, think about it this way. Let's say they were figuring out the rates of a given species, and let's say they did it at 20 degrees Celsius. Well, they continued to do the same reaction, the same experiment at a different temp, and so forth. So now they came up, not only does the concentration determine or affect the rate, but also temperature. And we have Arrhenius to thank, who came up with this proposal. The rate of the reaction is also affected by the temperature, and therefore the rate of the reaction is affected by the collision or the frequency of the collision of the particles. But what he found out is that only a small fraction of collisions produce an actual reaction. Why is this? Well, what he came up is that these molecules have to overcome a threshold, what we know as the activation energy. Even though there are collisions occurring right here, even though the reactions are taking place right here, it's not enough for them to continue until they've reached the activation complex or the transition state. And think of the transition state as the point of no return. All right. So we know that this side of the energy is the input, and this is going to be the output. So my rates of my reaction is not determined by the change in energy, only by the activation energy needed. So let's use an example of an equation. And let's say I have 2 BrNO molecules reacting with 2 NO. We're not reacting, it's producing 2 NO gas molecules and 2 bromine molecules. All right, so if we look back at our equation, let's say this is the same reaction progress of the given equation. All right, even though I have collisions occurring at this point and at this point, I do not have the sufficient amount of collisions to come out with the product or for them to decompose. Once I have enough activation energy, I can reach my transition state or my activated complex, meaning that I'm at a no point of return, and I have made a complex molecule where I am going to form bonds between my Br molecule and I'm going to break bonds between Br and nitrogen molecules. So what we can say is that in order to make a Br2 molecule, a bromine gas molecule, I need 2 BrNO molecules to break 2 bonds between my bromine and my nitrogen, just to make one bromine gas molecule. So when we look at the same reaction at a different temperature, the fraction of effective collision increases exponentially, meaning my frequency of collisions increase as I increase the temperature. So if I'm increasing my frequencies, eventually I will have one that will make it to the top. All right. So Arrhenius suggested that the number of collisions having an energy greater than or equal to the activation energy is given by this expression. All right. So he came up with his Arrhenius equation, and that the number of collisions with the activation energy needed is equal to the total number of collisions times the fraction of activation energy over the gas constant over times time. All right. So he did all this work to only find out that the observed reaction rate is considerably smaller than the rate of collisions that have enough energy to break the threshold. So what else is missing that is causing this effect? Well, this is where he came up that what else is required is the orientation of the molecules. So now we know that we have to have the right amount of energy, activation energy, the right amount of frequency of collisions, but also the right amount, the right orientation in order to break those bonds and form new bonds. So we know what determines the rates now is the orientation of the molecules, the activation energy, and the frequency of collision of the molecules. So what we can say now is that my constant, or my rate constant, K, is equal to the frequency factor times the fraction of the activation energy over the gas constant times temperature. And that is the Arrhenius equation.